Hello students, welcome you all. So today we will start the topic alkyl halides, and in alkyl halides we will see the detail of various nucleophilic substitution reactions and elimination reactions. Nucleophilic substitution reactions, for example, is SN1 reaction, SN2 reactions, SNI reactions, elimination reactions like E1 reactions, E2 reactions, and little more about that. Now, before starting the detail of these type of reactions, we should know the concept of nucleophile and base, or we can say what are the difference between this nucleophile and base, and what is the difference between nucleophilicity and the basicity. Now let's see the difference between the nucleophile and base. Before that, let's see the difference between nucleophile and this electrophile. Now then I will come to the base. So if we see this nucleophile, okay, and this suppose electrophile, I'm writing here the electrophile. Now, what are these nucleophile? All of you know this nucleophile, these are nucleus loving species. Or we say these are positively charged loving species. Okay, and these are electron loving species. These are positively charged electron loving species. These are electron loving species, or we can say negative charge loving species, just opposite to the nucleophile. Okay, or some other way we can, what we say, the nucleophiles are the electron rich species. These are electron rich species, and these are electron deficient species. These are electron deficient species. Okay, so electron deficient species, for example, if we say this tertiary carbocation, this is electron deficient species, or secondary carbocation, primary carbocation, and some electron deficient species, all of you know this aluminum chloride or aluminum trichloride, boron trifluoride. These are the electron deficient species, and these are the electron rich species. So this electron deficient species, all of you know this electron deficient species, these are also called as the Lewis acid. They are, so that's why we say these electrophiles are the Lewis acids. Lewis acids. Okay. Whereas if we see this nucleophile, then nucleophile, these are electron rich species, and which donate its electron pair to the electrophile, and usually at the carbon deficient center. So electrophile, we can also write that nucleophile, these are the species which donate its electron pairs to the electrophile, or we can say which attacks the electrophile. So this electrophile, these are usually carbon center. In organic chemistry, we are concerned with this carbon center. So nucleophile attacks at the carbon center to form a chemical bond, to form a covalent bond, to form a covalent bond. Okay, so this is this nucleophile. and because it donates its electron pair, that's why it may called as a Lewis base. Okay, so we know that the Lewis by acid-base definition, Lewis acid-base definition, or this Bronsted acid-base definition. By Lewis acid-base definition, Lewis base are the species which can donate its electron pair. So that's why, as they may donate its electron pair to the electrophile, that's why they may call as a Lewis base. So they are Lewis base. They are Lewis base. They are not Bronsted base. So they are Lewis base only. Okay, so this is about. So this is a little about the electrophile. We are not so much concerned here with this electrophile. We are concerned with nucleophile, and we will see about what are this base. What is the difference between this nucleophile and the base? Okay, so this nucleophile, it may be categorized into the three ways. So one thing which is clear, which is nucleus loving or positively charged loving species, electron rich species, and it means it must contain a negative charge, or it must contain this lone pair of electron. Okay, so some of the examples, if we see, for example, suppose this hydroxide ion. Okay, and this we may write this iodide ion. Okay, bromide ion. These may act as this nucleophile. It may act as this nucleophile. So these may act as a nucleophile because it contains this negative charge, or it may contain this lone pair of electron. That's why they are considered as a nucleophile. So better to categorize this nucleophile in a three ways. So let's see categorization of this nucleophile. And first type, nucleophile having lone pair of electrons, Okay, nucleophile having lone pair of electrons. For example, let's see. Suppose if we have any alcohol, and this alcohol, because it contains this oxygen having the lone pair of electron, that's why it can act as a nucleophile. And what I told in the definition, it may attack at a electrophile, that is carbon center. So suppose any electrophilic carbon center, suppose, so this may act as a electrophilic carbon center, positive charge center. So because this has the partial negative charge, and this carbon has a partial positive charge, so this may electron rich part can attack at a electron deficient part, and finally what we get one of the ether. We get one of the ether plus this chlorine. This chlorine will leave out. This chloride ion will leave out. So this chloride ion will leave out containing this electrons, and this is leave out. Okay, so this is a nucleophile here, having this lone pair of electron, and here this is the substrate molecule. We can say this is the substrate molecule. So this is a nucleophilic substitution reaction, which we will see in a detail later on. So this is one of the nucleophilic substitution reaction. Nucleophile is attacking on a electrophilic center substrate molecule to form a nucleus product, and plus this, because this chloride ion is leaving out, that's why it is called as the leaving group. This chloride ion is called as the leaving group, and we will see little more about the leaving group in my next lecture. Okay, now, so in the same way, suppose if we have ethylamine, and this ethylamine, it may attack any, suppose this is bromide. So here this acts as a nucleophile. This is a nucleophilic species, and this is a substrate molecule having this electrophilic center. So this carbon having this delta positive charge, partial positive charge, this has a partial negative charge. So here this bromide ion will leave out. Bromide ion will leave out, and what we will get? We will get here this product plus this bromide ion as a leaving group. This will leave out. So in this reaction, as you have seen, the nucleophile contains the lone pair of electron. The nucleophile contains the lone pair of electron. Okay. In the same way, suppose a second type that we can categorize, that is the nucleophile having pi bond, or we can say which can donate its pi electrons, pair of pi electrons. Okay, here the nucleophile can here donates the pi electron, pair of pi electron is donated here. Okay, pi electrons are donated. As the pi electrons are loosely held electrons, that's why it can easily be donated out in comparison to this lone pair which is present on the oxygen. Okay, so suppose if I have an example, suppose propene. This is a propene, and if it reacts with this HCl, then what will happen? So this all of we have read. This is one of the example of Marconic product. So here in this pi electrons are loosely held. As this pi electrons are loosely held, so this will having this delta positive charge, delta negative charge, and here this chloride ion will leave out, and here this hydrogen, okay, this proton that can attack either over this center or over this center, but this center is the secondary carbocation. It forms a secondary carbocation and it forms the primary carbocation. So the hydrogen, according to Marconic rule, that will add at that position where the number of hydrogen is less, at that carbon where the number of hydrogen is less. So here the number of hydrogen is more, and here the number of hydrogen is less. So the hydrogen will attack at this carbon where the number of hydrogens are less. So finally here the positive charge will come, and the one of the hydrogen will come over here, and plus this chloride ion, and this chloride ion will come over this positive center, and finally what we will get? We will get this product, isopropyl chloride. That would be the product. In the same way, so pi electrons, for example, were either the pi electrons, as you can see, this contains a double bond. So double bond may act as a electrophile, nucleophile. Triple bond may act as a nucleophile. And we know that this double bond is also present in aromatics. So aromatic compound like benzene can also act as a nucleophile, and some of the other compounds which contains the double bond may also act as a pi bond can act as a nucleophile. For example, this enol for enolate, and these may act as a nucleophile. In the same way, suppose if we have benzene. If we have a benzene, because it contains the pi electron, that's why it may act as a nucleophile. And suppose if we have a propyl chloride, and this, you know that electrophilic substitution reaction in presence of this aluminum chloride, what is formed? It gives rise to the formation of isopropyl benzene. Isopropyl benzene is formed, plus this is AlCl4. This acts as a Lewis acid here, so AlCl4 minus. So this is formed. I am not writing the complete mechanism of this electrophilic substitution reaction. Similarly, aromatic or this pi bond or some enolates can also act as a nucleophile. We know that this is the enol. this is enol, and if we see this, this is our enolate. This is the enolate. This is enolate ion. So enolate ion, if we say this is the enolate ion, and it may attack over the some electrophilic center, and suppose it is acetaldehyde. So this is our electrophilic center, delta positive charge. This has the delta negative charge. So here in this enolate ion we have the lone pair of electron also, as well as we have the pi electrons. So which part, we know that lone pair of electron also act as a nucleophilic part, and this pi electrons also has a, they also act as a nucleophile. So out of these two nucleophilic center in this species, so which will act as a nucleophile in this reaction? So no doubt which is able to donate its electron pair much easily, that will act as a nucleophilic center. So out of these two center, the nucleophilic center, that would be the pi bond. We know that this pi bond is the loosely held electron in comparison to this lone pair of electron. Lone pair of electron, these lone pair of electrons are not loosely held because they are in vicinity with the this electronegative oxygen atom, which can pull the this lone pair towards itself. So that's why this will not act as a will not act as a nucleophilic center. This will pi bond, this pi electrons will act as a nucleophilic center. So this will act as a nucleophilic center, and what we will get? We will get here and here we will get the positive charge, and at this center we are getting okay. So in next step, this positive charge that would be neutralized, and we will get such product. Okay, so this is the example where this pi bond act as a, or pi electrons act as a nucleophile. Now suppose if we have some groups which are present. So as I told, this propene, it acts as a nucleophile. This propene, the pi electrons of this propene act as a nucleophile. So suppose I am adding one of the group, suppose this is NH2, or I have suppose added one of the group, here is hydroxide, or we may have some another pi bond in conjugation with this, and similarly I have another group, suppose aldehyde. So aldehyde group is in conjugation with pi bond, and this OH group is in conjugation with pi bond, this NH2 is in conjugation with pi bond. Now out of this 4 species that I have written here, which will act as a stronger nucleophile? Which will act as a stronger nucleophile? So in comparison to this, if we compare with this one, so here again if you will see 2 nucleophilic centers are there. This pi lone pair electron of this nitrogen can act as a nucleophilic center, and this pi electrons being the loosely held electron in comparison to these electrons, so this will act as a nucleophilic center, and here again this will act as a nucleophilic center. So out of these two, when this will act as a nucleophilic center, then positive charge will be generated over this carbon, positive charge will be generated over this carbon, and this positive charge that will be neutralized by this lone pair electron, the delocalization of this lone pair. Okay, similarly this may also be neutralized, this positive charge, once it is created here, when this pi electrons are donated to the any electrophilic center, positive charge would be created over here, and this lone pair of electron will neutralize this positive charge or stabilize this positive charge. So here this species is much more stabilized, because here this lone pair are present on a less electronegative atom, where the lone pair is present on the more electronegative oxygen atom. So that's why these lone pairs are much loosely held in comparison to this lone pair. So that's why this will stabilize this positive charge much in comparison to this. That's why this is the more stable or stronger nucleophile in comparison to this, and in comparison. So these are electron, if you say NH2 group or this OH or this one, these are the electron releasing group. These are the electron releasing groups. Okay, NH2 group, OH, or this is the electron releasing group, whereas this CH aldehyde, this is electron withdrawing group. So this is electron withdrawing group. So if we see what is which is the more stronger nucleophile, no doubt, and this is much more stronger nucleophile in comparison to this. And at the last, this electron withdrawing group, where the electron withdrawing group is present, that would be the least strong nucleophile. Okay, so this is the second category. Now, third category that we can discuss, some sigma bond. Species having the sigma bond may also act as a nucleophile. So having sigma bond, or the sigma electrons or pair of sigma electrons can also act as a nucleophile, or sigma electrons can act as nucleophile. So usually such nucleophiles, they are seen in the reduction of a carbonyl compound. So for example, in reduction of carbonyl compounds, and where this lithium borohydride or sodium borohydride, that may act as a that will act as a electrophile, nucleophile. So if we have, suppose, sodium borohydride, so this is sodium borohydride, and if we have any carbonyl compound, so this is our carbonyl compound. So here it can, this sodium borohydride or this lithium borohydride can reduce this carbonyl compound. Okay, this can reduce this carbonyl compound, and here this sigma bond, boron hydrogen sigma bond, so this will sigma electrons will act as a nucleophile. Here hydride ion attacks this electrophilic center, okay, and that is being reduced. So what we may write? We may write this O minus, and here hydrogen is present over here. Another hydrogen which is reduced like this. So in this way, this sigma electrons, sigma bond, can also act as a nucleophile. So this is about the little bit about this nucleophile. Now let's come to so what I have told you about this nucleophile. Nucleophile which donate its electron pair, to the electrophilic center or carbon center, and they are usually Lewis base. So nucleophiles are the Lewis base. Okay, nucleophile are the Lewis base, which may have the lone pair of electron, which may have the pi electrons, or which may have this is sigma electron. Now let's come to the base. So now what are this base? If we see this base, now in this base, what we make call as a base. Base are also a nucleophile, or the base are the species which can donate its electron pair to the proton. So nucleophile donates its electron pair to the electrophile, whereas this base are the species, or these are nucleophile, we can say. Base are the species or nucleophile which donates its electron pair to the proton to form a covalent bond. Okay, so this is base. Okay, so here this proton is coming into the picture. In case of base. Now suppose if we have NaOH, NaOH and plus this HCl. So what we may write? So it can donate its electron pair to the proton. And what is formed here is Na plus and plus Cl minus and plus this H2 which is formed here. So here this NaOH acts as a base, but in previous I also told that this OH minus can also act as a nucleophile. So OH minus can also act as a nucleophile. Here this OH minus is acting as a base. Why it is acting as a base? Because it is donating its electron pair to the proton. So here it acts as a base. But if this NaOH is reacted with suppose some alkyl halide, then in that case that will act as a nucleophile. So we will see little more. So here it acts as a base. Now suppose in the same way, suppose I write reaction ammonia plus this water. So we know that this is a strong base. This is a weak base. Weak base plus this is suppose weak acid. Here this is a weak acid. H2O may act as a weak base or weak acid. So weak base, and it may donate its electron pair to this one H plus, and this OH minus is formed here. So what we can write? We can write ammonium ion is formed here plus what is formed? This H3O plus is formed. Okay, so here this is acid-base reaction. And one thing that we can see here, this is the equilibrium reaction. This is a reversible reaction, equilibrium reaction. And in equilibrium reaction, we can find the value of pKa. So this pKa, so suppose we find the value of equilibrium constant, because this has the equilibrium. That's why we can find this dissociation constant for this reaction. We may find the dissociation constant of this reaction, that is called as the Ka. Or we may find the value of Kb. Okay, so Ka, what is the Ka? Ka is the concentration of products divided by the concentration of reactants. So from this Ka, we may find the value of Kb also. So indirectly, so such type of reaction where this acid such type of acid-base reaction, with the help of this acid-base reaction, we can also determine this relative stability of this acid and base. We can determine the relative stability. We can also determine the relative strength of this acid and base reaction. So as we can see here, these protons are involved. As we can see, the donation of proton or the gain of proton or loss of proton is involved here. This is a proton is lost here, or in some reaction, in some acid-base reaction, the gain of proton is involved. So such concept what I told you, this is nucleophile are the Lewis base, and that is the Lewis base concept. Nucleophile is the Lewis base. But here, when we talk about the base, then this is, and we talk about the acid base reaction, and in acid base reaction the loss of proton and gain of proton is involved. So that's why this concept is the Bronsted acid. So these are Bronsted base. These are Bronsted base. Okay, these are Bronsted base. It means if these are Bronsted base, then what is acid? And we know, according to this Bronsted concept, the acid, what are called the acid? Acid are the species which donates or lose proton, which lose H plus, and base which gain H plus proton. And what are conjugate corresponding to this acid in Bronsted acid base concept? Corresponding to the acid, what is formed? Conjugate base is formed. And this conjugate base is the what which is left when the acid is, when the proton is when the loss of proton, after the loss of proton, what is left when acid lost the proton? So that is called as the conjugate base. So what is left? What is left when acid lose a proton? So in this case, when acid lose proton, that is called as the conjugate base. Okay. In the same way, conjugate acid. If we say conjugate acid, what is conjugate acid? What is formed when a base gains a proton? So what is formed? So it is clear. 1 minute, that will be clear. What is formed when a base gain a proton? Okay, so if you see in this definition, if you see in this case, this is weak base, and corresponding to weak base, what is formed? Conjugate acid is formed. So this is the conjugate acid in this case. This is conjugate acid, and this is the conjugate base.